Okay, guys, we're picking it back up on the practice test 3 multiple choice test. So we stopped off, we're on question 33 out of 50. So hopefully this video will get through it. All right, so this is talking about percent ionization. And we want to know what would increase the percent ionization. So if you're thinking in terms of Le Chatelier's principle, we want to cause a shift to the right. But one thing we have to know about percent ionization is all it is if you have an acid, a weak acid that doesn't, fully ionize, it doesn't have 100% ionization. What it would be is the amount of H plus you get divided by the amount of acid you start with, right? So let's say I start with 1 molar HF and I end up with, zero point 0.1 molar H plus. Then I would just do 0.1 divided by 1 times 100, and that would give me the percent ionization of the acid. So let's understand one thing. So the stronger the acid, the higher the percent ionization. But also, if you do the math and you sit there with different acids with their same Ka value, what you'll notice is as the concentration of the acid increases, the overall percent ionization decreases. So as the concentration of the acid decreases, percent ionization will increase. So yeah, if we cause something to drive the reaction to the right, but doesn't affect the initial amount of HF, then that could increase percent ionization. But another way to think about it is if we dilute the HF, we're going to get a higher percent ionization. So if you notice, the correct answer there is add distilled water. If you add distilled water, you dilute everything. But if you have a lower concentration of HF, you're going to end up with a greater percent ionization. Yes, if you have more HF, if you add more HF, you're going to drive the reaction more this way, but your starting point is higher, and then your overall percent ionization actually is less than what it would be if it was a lower concentration. Notice that adding fluoride would drive the reaction that way, common ion. Adding sulfuric acid would add more hydronium, and that would drive the reaction that way. So the only thing that works here is D. Okay, so let's keep on rolling. All right, here we got these 3 reactions, okay? And it doesn't matter that this is a demonstration called underwater fireworks. Just answer these questions. All right. So calcium precipitates, calcium hydroxide precipitates when 1 gram of calcium carbide is added to 1 liter of distilled water at room temperature. Okay, so if 0.064 grams of calcium carbide was used instead, would we still get a precipitate? So this is going to be a QSP equals, or comparing QSP to KSP. And so what we need to do is figure out, based on this reaction, okay, how many moles, if we start with 0.064 grams of calcium carbide, if we go times 1 over 1, that'll give us how many moles of calcium hydroxide would be produced. So we have 0.064 divided by 64. That comes out to be 0.001 moles. Now, the volume of the whole solution is not exactly 1 liter, but it's going to be close to 1 liter. So let's just assume that's our molarity. So if we plug in those concentrations, the calcium would be 0.001. And I just realized I made a mistake here. So, hey, and no one's perfect there. So the concentration for calcium would be 0.001, but the concentration for hydroxide, I should have 0.002 here. So QSP is not 1 times 10 to the negative 9. This should be 0.002 squared. So it comes out to be 4 times 10 to the negative 9, which is still less than the KSP, 10 to the negative 9 versus 10 to the negative 8. So the answer is still right. I just, if this was free response, I wouldn't get the point. Uh-oh. Okay. So, hey, there's a common mistake people make. I just made it. All right. So let's go to number 35. Reaction 2 occurs when an excess of 6 molar HCl solution is added to 100 milliliters of a sodium oxalate, not oxalate, a sodium hypochlorite solution of unknown concentration. If the reaction goes to completion and 0.01 moles of chlorine is produced, then what is the molarity of the sodium hypochlorite solution? So we just have to figure out, so if 0.01 moles of chlorine were produced in the second reaction, it's a 1-to-1 ratio with sodium hypochlorite. So that tells us how many moles. So we had 0.01 moles of sodium oxalate, and the volume was 100 milliliters. So divided by 0.1 liters. So 0.01 moles divided by 0.1 liters, we get 0.1 moles per liter. Okay. And then number 36 is just asking us to look at this and what happens to the hybridization of carbon from C2H2 to C2H2Cl2. So you might want to draw out the dot structures. Here's C2H2, and here's C2H2Cl2. Now, it doesn't matter if you draw the chlorines on the same side, or if you draw them on opposite sides, or if you draw the cis versus the trans. All that matters is the carbon has 3 domains here, and it only has 2 domains here. So it's sp hybridized here, and it's sp2 hybridized there. So A is our answer. Okay. All right, so we go to 37. So we're given the Kas for these two acids. Notice that this Ka is a lot higher than this Ka, so we know that they're both weak, but this is the stronger of the two. But this question is asking us to make a buffer with a pH close to 3. So remember, the pH is going to be close to the pKa of the acid. All right, so the negative log of this versus the negative log of that. So we want a buffer that's close to 3. Now, we don't have a calculator, so I can't take the negative log of this. Okay, but remember, when you take the negative log base 10 of something, it's close to that exponent. So this is going to be a pH around 4, maybe, or maybe a little bit less than 4, but close to 4. And this would be a pH close to 11. So I know I'm not going to make this buffer system. That's going to maintain a pH closer to 11. This one will be closer to the desired pH that I want. Okay. So we got to figure out which of these procedures would make a buffer out of these two. So we would need this, and we need its conjugate base. Now, remember, the other way to make a solution, a buffer solution, is take an amount of weak acid, and if you add strong base to it, as long as the amount of strong base is less than the amount of strong acid, you'll make a buffer. So here we have 100 milliliters, 0.1 molar acid, 50 milliliters, 0.1 molar strong base, sodium hydroxide. So the resulting solution, as the hydroxide reacts with this, you're going to get its conjugate base, and that would be the buffer that we want. So B. All right. 38. The Lewis electron dot diagrams for the two acids are there. Which one's the stronger acid and why? The more oxygens you got, the stronger the acid. But we should know that we call chlorate a strong acid, and so we should know just right off the bat that it's got to be the HCl3. So we can eliminate C and D. Now the reason that is because the real reason is because the extra oxygen. So like you have two oxygens kind of pulling the electronegativity pull on this bond here, and so it's easier to remove that hydrogen because you have 3 oxygens on this side of the molecule pulling on that bond, versus here you only have 2 oxygens on this side of the molecule pulling on the bond. So it's going to be a little bit tougher to remove that hydrogen than it is that hydrogen. But they're saying it because it stabilizes the conjugate base, and I guess that's an answer, but the majority of times they ask about why is this polyatomic ion acid stronger than that one, and it's because it's more oxygens, and it's because of the greater electronegativity pull on the bond. So watch out for that. All right. So that's B there. All right. So 39. If equal masses of the following compounds undergo complete combustion, which will yield the greatest mass of CO2? So you're looking for a hydrocarbon that has, or you're looking for a compound, organic compound that has the highest percent carbon by mass. So if you notice, like C6H6 versus C6H12, this is going to be higher carbon by mass. If you throw some oxygen into it, that's going to be even less carbon by mass than this compound. So of these three, I know that this has a higher percent by mass. So it comes down to the benzene versus the methane. So it's 72 divided by 78 versus 12 divided by 16. And we got to know that 72 divided by 78 is going to end, times 100 is going to be a higher percentage than 12 divided by 16 times 100. So A is going to be our answer there. All right. Here we have to, delta H is positive. So I immediately circled that and I put heat as a reactant. So this is going to ask, which of the following will decrease the amount of COS in the system? So COS is a product, so we got to drive the reaction to the left. So for an endothermic reaction, that would be lowering the temperature, so that's why it is B, okay? So increasing the temperature would shift it that way, and I get more of that. Removing CO2 would cause it to shift that way to replace the CO2, and I'd end up with more of that. Removing solid CaCO3, remember adding or removing a solid directly does not cause a shift, so watch out for that one. So I bet a lot of kids pick this one because they forget that Le Chatelier's principal trick. Adding a solid or removing a solid doesn't cause a shift, but so the key to here was understanding, positive delta H, endothermic, lowering heat is going to cause it to shift to the left, all right? All right, so if you read this question, we're looking for an acid that has a molarity between 0.2 and 0.3, and they take 4 100 milliliter samples of the acid, and they react it with 0.2 molar NaOH. So if our target is 0.2 or higher, then we need, and it's, they're monoprotic, so 1H plus, and the base, sodium hydroxide, is 1 hydroxide. We're going to need an acid that takes 100, a little bit like 100 milliliters of NaOH, because if it takes 100 milliliters of this NaOH solution to neutralize 100 milliliters of that solution, then the molarity is going to be 0.2, and we need it to be 0.2, maybe even a little bit more. So we know it's going to be the acid that took 115, because that, if we do MAVA equals MBVB, we would get, if we use this volume, we would get one that falls between there, okay? But again, in your head, if the base takes the same volume as the acid I started with, the acid is gonna have the same molarity. So I'm looking for 0.2 or higher, so I'm looking for at least 100 milliliters, okay? All right, so now we got some kinetics. So here we got a reaction mechanism. So let's just highlight some things. Chlorine in this mechanism is a catalyst because it cancels out this way, right? It gets used and then produced. And the ClO is an intermediate. We never include intermediates, but we would include a catalyst if we have one, and we do have a catalyst, so we will include that. And it's just asking us, based on this overall reaction mechanism, what is the rate law? So please, 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 never select D when you're finding a rate equation. You don't have a denominator, okay? And so we can only use the slow step and any steps beforehand, but since the first step is the slow step, that's the only one we're going to use. Ozone shows up once, so it's first order, and chlorine shows up once, so it's first order, so B. They're both first order, okay? If it was if this were the slow step, then the right answer is not up here. The right answer would be O3 is second order and chlorine is first order. That's not a choice. Remember, don't use an intermediate. So I immediately cancel out this one. I should immediately cancel out that one because it is including an intermediate, and that can't be right. So I got a 50-50 shot if I don't remember what to do, but should be easy enough. All right. All right, this one corresponds to, right, so 42 through 44 refer to this mechanism. And so if we go back here, we know it's exothermic, and we know the slow step is the first step, so the slowest step has to be the rate determining step. So first off, we know we can cancel out D because that shows an endothermic process, okay? So C would work in terms of exothermic, B would work in terms of exothermic, and A would also work in terms of exothermic. But we need two humps because we had two steps, so we know it's not A. And then it's got to be the one where the first hump is the highest, not the highest, but the highest from the starting point to the top of the hump. So this has a higher activation energy than that, but this from here to here is a higher energy than from here to here. So B, because that would be the first step is the slow step, right? And then here we have that same mechanism, only X, or chlorine is replaced with X. So what else could we use instead of chlorine? Well, something in chlorine's group, so bromine, periodic trends. All right, let's keep going. So KQ here is greater than 1. So we know the forward reaction is more favored than the reverse reaction. So these two acting like acids and bases is stronger than these two acting like acids and bases. So HX is a stronger acid than HY, and Y minus is a stronger base than X minus. So if this had been less than 1, then this side would be stronger. But since this is greater than 1, we know this side is stronger because this acting like an acid going this way is more favored than this acting like an acid going that way. So this is asking what's the strongest base, and the two bases of the reactions are Y minus and X minus, and since the forward reaction is favored, it's Y minus that's the strongest base. If the reverse reaction were favored, it would be X minus is the strongest base. Okay. Okay. So we start with 0.1 molar X and 0.1 molar Q. And our K is a pretty big number, a lot greater than 1. And we want to know at equilibrium which of the following is true. Okay, so we know that since we didn't start with any R and Z, we know R and Z are going to be equal to each other. And we know that they're going to be a lot greater in terms of concentration than Q and greater in the concentration of X because products are favored, or heavily favored at equilibrium because we have such a high equilibrium constant. Okay, so none of the other things would hold true, so it would be C. Okay. All right, so 47, we have a potential energy diagram, but not a reaction coordination diagram. This is bond energy. And so remember, right here, if we were given this would be negative potential energy, and that would be the amount of energy released when the bond is formed. And over here, that's the internuclear distance, so that's the bond length. And what we're trying to show you is if we have two atoms that are forming a bond, the nuclei are, when they're really far apart, there's no interaction at all. But as the two atoms get closer and closer and their nuclei get closer and closer, you're stabilizing, you're maximizing attractive forces and kind of minimizing repulsive forces. But if they start to get too close together, the positively charged nuclei are going to start to repel each other. So you have attraction, attraction, attraction due to the stabilizing characteristic of their both their electron configurations being like satisfying the octet rule. But then if they get too close to each other, now you get that repulsion from the nuclei from each other. So this is the sweet spot. So right here would be the bond energy, and right here would be the bond length, and the attractive and repulsive forces are balanced so that the atoms will maintain an average internuclear distance, which means bond length. So right there. All right. All right, so here we have a reaction, and we got to be careful. We look at this and we're like, oh, okay, I'm gonna look at these two, and I'm gonna say, okay, I doubled the concentration of X, and the rate quadrupled, so X is second order, which is true. And then if I look here and here, I doubled the concentration of Y, and Y turned out, and the rate also doubled, so Y is second order, which is true. So it's good to see that. But all it's asking is, in trial 2, which reactants would be consumed more rapidly and why? So this really has nothing to do with this at all. It's just you're going to lose Y twice as fast as you lose X, no matter what the trial. For every one X that gets consumed, you lose two Y. So 2 is going to be consumed faster than Y. Or 2. Y is going to be consumed faster than X. Always, because of that stoichiometric ratio. So the answer is D. Why? Because the rate of disappearance will double that of X. Always. Always. Okay. All right, so here we got some paper chromatography. And so what we got to understand is the surface of the paper is polar, but if we look at what we dipped the paper in, hexane, we got to know that hexane is nonpolar because it's a hydrocarbon. So what's happening here is you're dipping the paper into the solvent. The solvent's going to travel up the paper, okay? And it's going to go through this ink dot. And if the ink dot is a mixture of two different things, they're going to start to separate based on how fast they move with the hexane versus how they interact with the paper. So let's think about this. The paper's polar. So if something's polar, it's going to interact with the paper more than it interacts with the hexane. So it's going to not move as far because it's attracted to the paper and it's not attracted to the hexane. But if it's nonpolar, it's not going to interact with the paper that much, but it will interact with the hexane, so it's going to move further. So just right off the bat, I know X is probably nonpolar or not as polar as Y. Y is more polar because it didn't move as far, and X would be nonpolar because it moved further, or it would be more nonpolar than Y. Okay? So that's the way to think about this. What can be concluded about X and Y based on the experiments? Y is more polar than X. Yes. All right. I hope that makes sense to you. All right. Now, the very last question. Whoops. I didn't have it on the key. Hold on. I'll pause. So I remember why I didn't include it on the key, because I wanted to stress this kind of point here. This question, I've never seen a question like this on any AP exam ever, except for this practice test. And remember, these practice tests are based on the international exam, and there's a few standards that the international kids have that we don't, and a few standards that we have that they don't. All right. So this is not really covered in AP chemistry in America, but we could hopefully figure it out. Okay. So it's saying here's some absorption spectra. So I want us just to understand the light. So this is a good review on light. So this is higher energy light, lower energy light, and even lower energy light. So ultraviolet has more energy than infrared. Infrared has more energy than microwave. Okay. And it's saying which of the following correctly indicates the type of transition observed for the substance in each of the regions of the absorption spectra. So it's really like what takes more energy. And so the three things we're looking at is making a molecule vibrate more, making a molecule rotate, so just kind of rotate in space, and making an electron jump from a higher energy level from a lower energy level to a higher energy level. Okay? So the thing that takes the most energy out of those three things is electron transition. Okay, so I know region X, the higher energy light, is being absorbed by electrons. That's electron transition. So it's either D or B. Okay, so I can cancel out A, I can cancel out C. All right, so what do you think? To make the particle vibrate more, or to make the particle just rotate is going to take more energy? And to make it vibrate more is going to take slightly more energy. So that's infrared. So I know the answer is D now. And then the lowest energy thing there is just making the molecule rotate. Okay. But again, I want to stress this. Remember, there might be one or two questions on the AP exam that you just see it and you're like, I have no idea. And you can, curse me under your breath and say, I didn't learn this. This was never presented to me. And that's great. And I totally understand how angry you could be. But also just understand that, okay, don't let it phase you. Remember the goal, 79%. and you get a 5. So one question is not going to break you. Don't shut down when you see a question like this if you haven't ever seen it before. Just take your best guess and move on. Okay? Make note of it and come back and talk to me about it and say, hey, you know, I saw this question. It was, And then a lot of times when kids do that, I saw this question I didn't know, and I just go, oh no, that's just an acid base, and they go, oh. So remember, there's going to be things that are presented to you in a different way just because, you know, maybe you didn't take a lot of practice tests, or maybe you took all the practice tests, but again, College Board has to write a new test every year, and they always are trying to figure out ways to trick you and lead you down the wrong path and that kind of thing, because they want you to have mastered the concepts. So, you know, again, don't freak out. Just take your best guess and move on. Okay? Goal is 80%. 79%. Most years, 79% will give you a 5. I don't think I've ever seen an 80%. But some years it could be a 75, a 72. So we'll see. We'll see how this year goes. But you know, don't freak out. You see a question you don't know the answer to, and you have no idea, take a guess. All right. So anyway, that's it. We did the whole multiple choice practice test. Hopefully that helps, and later.